Hello and welcome to another video. In this video we're going to be going over all the problems from the weekly contest 393 for today. And so let's get started. So in the first problem it's pretty easy. You're given a time and your hours or minutes can be question marks or times, and you want to return the biggest time you can get. So basically this is just a straightforward, like a bunch of if-else statements. There's not really too much to say. So like if the first thing is a question mark, you basically check if the second one is either a 1 or a question mark, it has to be, so the biggest time you can have for hours is 11, right? So as long as this second hour is less than 1 or a question mark, you can make the first hour 1, and then similarly for the second hour, you check if the first hour is what it is, and then that's the most it can be. So if the first hour is a 1, then the second hour can only be a 1, and that would give you the biggest. And if it's a 0, you just make it a 9. So pretty straightforward. And then for minutes, they don't really affect each other. So for minutes, basically, you just always want to make it 59, no matter where the question mark is. So if you have like this, you want to make this a 5. If you have 5 question mark, you always want to make this a 9, and so on. This is just, you always want to make it 59, because that would give you the biggest. So pretty straightforward there. There's not really too much to talk about. So let's go into the second one. So the second one is also pretty easy. They basically tell you there's also not too much to talk about. So you have a bunch of numbers, and you want to return the maximum distance between the indices of 2 prime numbers in nums. And you have 10 to the 5th numbers. So you basically just need a somewhat efficient function to figure out if a number is prime. Now there are some optimizations here that I'll talk about. So because your numbers are only 1 through 100, you actually want to just cache results, because your array is 10 to the 5th numbers and your numbers are 1 through 100. So you're going to have a lot of repeated numbers. You can actually use, there's something called like the sieve of Aristophanes or something, I never pronounce it correctly, to get this faster. But because there's only 100 prime numbers, like your prime number function honestly doesn't even have to be that efficient. Like you can literally just, you don't even need to do this. You can just go through like every number up to the number and see if it's divisible, and that would work as long as you cache. So you basically just have a function to check if a number is prime, cache the results, and then the rest of it is pretty straightforward. So you just go through the array, and the indices you want are the index of the first prime number and the index of the last prime number, and those are the two that you'd want. So in this first example, the first prime number is here and the second prime number is here, but that's going to give you the biggest like distance. So that's all I did here. So I said if the number is prime, if left is not there, then make it left, and otherwise just keep updating the right index to give me the rightmost. Then I just do right minus left, so the rightmost prime number minus leftmost prime number. Like I said, this doesn't even have to be super efficient. You can have O of n function to determine if a number is prime, because there's only 100, but caching will make it significantly faster. So I don't even know if this actually had good runtime. It had okay runtime, but let's say we get rid of this cache. Let's see what happens now. I would predict it should be significantly slower. Well, it's actually not too different, but yeah, I guess it depends on the test cases and so on. But basically, yeah, you have a ton of repeats, so definitely. And yeah, you can do the sieve of Aristophanes or whatever it's called. It'll do this a little bit faster. The idea with that is you give it a range of numbers, and then you can determine what numbers in that range are prime. And it's going to be a little bit faster than that, but because there's only 100, it doesn't really matter. Okay, now let's get into the interesting ones. So here's the third one. So you have the kth smallest amount with single denomination combination. And you're given an integer array coins representing coins, and an integer k. You have an infinite number of coins of each denomination. However, you're not allowed to combine coins of different denominations. Return the k smallest amount that can be used. So for this one, you actually need to know a decent amount of stuff, and there's like one thing I was missing. Like I got pretty much all of it, except I was missing one thing. So let's just first go through an example of where all the coins are, like, there are no coins that overlap. Like here, there's coins that overlap. Like for example, 3 will overlap, and the 9 will overlap, right? So 3 times 3 will give you 9, and 9 times 1 will give you 9. But let's say you have coins that, I mean, I guess these overlap too, but they don't overlap for, I guess technically no matter what you have overlap, right? But let's say for example we counted, like we are allowed to count duplicates twice. Let's say we had that problem. So let's actually go through this one, and let's say we are allowed to count duplicates twice. So they tell you like these are all the coins, but instead let's say our coins would be like, so for 2 we could make 2, 4, 6, 8, 10, 12. And then for 5, we could make like 5, 10, 15, 20, and so on. And let's say we count the overlap twice. In this one we don't, but let's say we did. So our first 7 coins would be 2, 4, 6, 8, 10, and then 5, 10. So it'd be like this order. If we threw these in 5, 10. So how would we solve that? That's going to be like the easier version of this problem. So to solve this, and we would need like something like this, right? And so our answer here would be the 7th coin would be 1, 2, 3, 4, 5. You should get the 10 here. So to solve this is going to be a lot easier, and to handle the overlaps is like the hard part of this problem. But let's say we were just solving this. First of all, they give you a kind of hint. So k is 10 to the 9th, which means you basically know you kind of need to do a binary search, because you can't, like, linear will be too slow, so binary search is kind of like the only thing you can do. So now that we know that we have to binary search, like, what are we binary searching for? We're basically binary searching for an amount, and then for a given amount, we can figure out like how many amounts can be made, like, that are less than or equal to that amount, right? And then the answer is going to be the smallest amount that gives us k or more. So let's kind of walk through that and why that is and so on. So this actually wouldn't be 10, 10, 12, 20 if we have duplicates. This would be 10, 10, 12, 15, or actually 14, 15, 16, 18, 20, 20. So this is fine with duplicates, and then we'll figure out how to get rid of duplicates, because like they show here, you don't want duplicates. So what are going to be our bounds for our amounts? So the bounds for the amounts are going to be, let's just say like the left is 1. You could probably come up with something better, but this is fine. And then the right is going to be like what do we know for sure? Like, what amount do we know for sure will give us will give us something that, you know, there's k or more. Well, we actually know for sure that if we just take the smallest amount of coin and multiply by k, which is 14, we know for sure our answer won't be higher than 14, because obviously if we literally just use the smallest amount of coin, there's five different amounts there, right? So, or not 5, there's going to be 7, right? So it's going to be like 2, 4, 6, 8, 10, 12, 14. That's 7. So we're guaranteed, if we just do the smallest coin times 7, or times k, to have an upper bound. But there might be other numbers in there, right? Because if we have other coins, so we have like two, let's say we have like 5s and 3s and so on. Like we have a 5 here, we have a 10 again, we might have like a 3 and some other stuff. But this is guaranteed to work for an upper bound. The lower bound, maybe you can think of something better, but it doesn't really matter too much because it's binary search. So essentially what we're saying is, for a given amount, we're basically trying to figure out, yes or no, do we have greater than or equal to k amounts, or like, I guess, do we have a different, greater than or equal to k amounts we can make using this, right? Using this amount. And so, for example, let's just walk through this. So let's say we pick a random thing, like we get a pivot value like 10. How do we figure out how many amounts we can make? So the amounts we can make, it says that we have to use 1 coin. So the amounts we can make with 10 is we can either use coin 2, and how many different amounts we can make with that. So the amounts you can make is basically just the amount you picked divided by the coin you're using. And you do that for each coin. So if we only use 2, we can make 2, 4, 6, 8, 10. Similarly, let's say we didn't pick 10. Let's say we picked 11. So we can make 2, 4, 6, 8, 10, right? Using 11. Because basically, yeah, like if the amount we picked was 11. Now 11 wouldn't quite work, but this would still work in our binary search. So you can also have a constraint. This actually has to be divisible by the thing, but that doesn't really matter. So basically, yeah. So we do have to check, like, if it is a valid amount. In this case, 11 wouldn't be. But then we would just, if 11 works, we can just keep lowering our number for the lowest number that's greater than or equal to k, and that's going to guarantee to give us the result. So for 11, we can make 2, 4, 6, 8, 10, which is 5 amounts. And then for using coin 5, we can make 5 and 10. So for using 11, we can make 7 different amounts. So for 11, we would return true. And then, so if for 11 we can make that amounts, we're trying to get the smallest amount where it's possible. So then we have to go 1 through 11. And just to speed up the process, 10 is going to be the smallest number that this will work for. So when we plug in 10 again, for 10, how many coins can we make with 2? So it's going to be 10 over 2, which is 5. And then how many coins can we make with a 5? It's 10 over 5, which is 2. And so that will give us seven different amounts. So with 10, we can make 7 amounts. And if we try smaller than 10, like let's say we try 9, then 9 over 2 is 4, and 9 over 5, and we do a floor divide, is 1. So then we only have 5 amounts instead of 7, so it doesn't work. So basically, you just do a binary search, and you have some kind of equation that tells you like how many amounts can I make total, and to figure that out, you just take your number that you are guessing and you divide that by each coin, and that would tell you how many amounts you can make with each coin. You add all those up. But there's a problem here, right? Because like I showed, so for this one, you actually don't want to return 10, you want to return 12, because for 10, yes, this does work, right? For 10, there are these 7, but the problem is these are duplicates and you don't want to include them. So how do you get rid of duplicates? And this gets kind of complicated. Like for only 2 coins, it's pretty easy. Like let's say we just have 2 coins, right? We have coins 5 and 2. How do we get rid of duplicates? So for 2 numbers, you're going to have a duplicate whenever you hit their LCM. So for 5 and 2, whenever you hit a multiple of 10, you'll hit a duplicate, right? Because if you look at multiples of 2, it's like 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then for 5 it's going to be like 5, 10, 15, 20. So whenever you hit a multiple of 10, you hit a duplicate, right? You hit a duplicate here and a duplicate here. So it's pretty easy. You can just take your number that you have, get the number of coins you can make with 2, the number of coins you can make with 5. So in this case for 10, you can make 5 coins with 2, 2 coins with 5, so you'd have 7 total. And then you'd have 1 duplicate because you could just say like, okay, every 10 I have a duplicate. So I can just take my 10, divide by 10. So it'll be like this, right? 10 over 2 plus 10 over 5 minus 10 over 10. And that would give you 6 amounts you can make. And then when we do this with 12, we get 12 over 2 plus 12 over 5 minus 12 over 10. And that would give us 7, and that's the smallest number that would work. Right? So this is 6 plus 2 minus 1, so 12 would be the answer here. But this gets really complicated once you have like 3 or 4 different coins. Because with 3 or 4 different coins, the number of duplicates you can make isn't really straightforward. So that's the one thing you have to know. So one thing you have to know is, the LCM. And LCM is pretty easy, so you can look up LCM. LCM is just, so the LCM of A and B is A times B over GCD of A and B. So like in this case, it'll be 5 times 2. And then over, so the GCD here, I believe, is like 1, I think. So this would give you that. LCM is also, the other way you can calculate it is you can get all the factors of a number, of both numbers, and then basically your number has to include all of those factors. So because 5, the factors are 1 and 5, and the factors of 2 are 1 and 2, your number has to include 1, 2, and 5, which would give you 10. So there's a bunch of ways. You can look up how to calculate LCM. Also, Python has a built-in LCM. Python also has a built-in GCD. And then to get the LCM of multiple numbers, you just do the LCM of 2, and then you add the third one, and so on. So if you want like 2, 5, 9, you would get the LCM of 2 and 5, and then you would do the LCM of that with 9, and so on and so on. So one optimization I made that you can do is, let's take a look at this example. What are the duplicates we're going to have? So here, if we have a number that's a multiple of another number, the bigger number is always only going to make duplicates, right? So let's just say like for 3, it'll make 3, 6, 9, 12, 15, 18, 21, 24. And 6 will make 6, 12, 18, 24. So you can see for 6, because 6 is a multiple of 3, every number that 6 made is only a duplicate. So basically everything for 6 is useless. Same thing for 9, so it'll make 9, 18, 27, which are all duplicates. So one optimization you can make is for your coins, any number that's a multiple of any other number, just get rid of the bigger number. So that's like an easy way to do it, because that will get rid of a bunch of your duplicates. But you will still have numbers like 5 and 2, and those will still have numbers that actually are duplicates, like here, right? And you can have multiples, so you can have like 2, 3, 5, and you can have a bunch of duplicates here, right? So like, let's say every time you hit a 6, that's a duplicate. You know, every time you hit like a 15, that's a duplicate, and whatever. So basically, so the generic formula that you need to know, and it's called the inclusion-exclusion principle, I think. So if we have two things, this is kind of like with sets as well. So if we have two things, A and B, and we want, so what we want is the items in here and the items in here. But we don't want the items that are in both. We want the items that are in both to be calculated once, right? Essentially. So that's pretty much like what we want to happen. And so the way to do that is, if you do the items, if you think about it, if you do the items in A, right? If you just do A plus B, then this section gets calculated twice, because this section gets calculated once for A, once for B. So to get this section to be calculated once, you would do A plus B minus A and B, right? And that's kind of what we said here, where you get the LCM and you subtract. So that's true for two things. But if you have three, so let's add a third thing here. So now we want kind of the same thing, where we want every single one of these items to be calculated once, right? Like we want this area to be calculated once, we want this area to be calculated once, this area to be calculated once. But you can see that, like, if we just do A plus B plus C, for example, right? If I do A plus B plus C, this area will get calculated 3 times. This area will get calculated twice, twice, twice. So to get all of these to be calculated once, you actually need to do A plus B plus C minus A and B minus B and C minus A and C, right? And there is one more. So let's say I have this. So in this case, so for right now, when I just do A plus B plus C, this gets calculated once, this gets calculated once, this gets calculated once. So if I do minus A and B, so A and B is this whole thing, right? So what will happen here is, now this will get calculated once, and this will get calculated, and this will get calculated 2 times. So let's see if I can get rid of that. Probably just to write in here. Now I do minus B and C. So B and C is, let's see, this region here, right? So this will go down to, yeah, I think what I'm doing is correct here. So let's see if I can select it. Can I? Yeah, there we go. So this will go down to 1. Nope. This will go down to 1, and this will also go down to 1. So let's see if I can select this. Yeah. So this will go down to 1. Now we do minus A and C. So A and C is this region here. So now this, you could see, will go down to 0. And this will go down to, if I can ever select it. So hard. Can I click on it? Okay, there we go. So this will go down to 1. So we almost have what we need, but now we need this. We need to actually add this region back in. So what we need to do here is we need to add A and B and C. Then this will go to 1, and that would be correct. So that's kind of the idea of the generic case. Basically, what you need to do for and how to do this with LCM. So essentially, if this gets converted to LCM, so you just say, like, okay, give me all the A's, give me all the B's, give me all the C's, minus LCM of AB, minus LCM of BC, minus LCM of AC. And then finally plus LCM of ABC. And that would give you everything counted once. And so that's kind of the generic case. Is basically you for all your coins, you have to do like all combinations. So there can be like 5 coins, right? So if there's 5 coins, you would do like you know, let's say our coins are called like A, B, C, D, E. So you do like A plus B plus C plus D plus E, and then you would subtract all combinations of 2 coins, and then you would add all combinations of 3 coins, subtract all combinations of 4 coins, and so on and so on and so on. So that's kind of like the generic case. And so basically, I guess you can write that as like 4x coins. What you do is you add all of 1 coin, subtract all combos of 2 coins, add all combos of 3 coins, and so on and so on and so on until you get to x. And so what you can actually do is you can pre-compute these ahead of time. So for example here, like let's say, obviously, like I said, in this thing, you can take this and you can just make it go down to 3. But let's say you have 1, 2, 3, 5. So you can't, like, none of these are multiples of each other, so you have 4 coins. So basically what you can do here is you can actually just store a bit mask of like which coins here are on. So for example, let's say our bit mask is like 0, 0, 1, 1. That means these 2 coins are active. And then you can just calculate an LCM here. So you can just do a bit mask for all of these. So you can just say, like, let me go in the range of 1 to 2 to the 2 to the number of coins. And I think this would be like this would be correct because, yeah, this is correct because it doesn't count the last one. And basically for each one of these bit masks, you just calculate an LCM. And then if your number of coins is if your number of coins is odd, then it's going to be positive, and if your number of coins is even, is negative. And then you don't even need like a hash map. You just need all of these values. So for example, for just 1, the LCM would be like 1. For 2, the LCM would be 2. For 3, it'd be 3. For 5, it'd be 5. For 1 and 2, it'd be 2. And so on and so on. So you have this array of LCMs where some are positive and some are negative. And then whenever you have a number you're testing, you just go through this whole array, and for every positive number, you divide your current guess divided by the number. And then if it's negative, then you subtract, and I'll kind of show that in the code. But that's kind of the idea. So you use LCM and this like set theory thing where, yeah, I think it's literally called, you can look up a bunch of solutions here. I think I was looking at one of it's called like, let me see if I can find it. This third one, it's like all the same. Let's see here. Inclusion-exclusion principle. That's the thing you can look up. So that's basically the idea of, if you have a bunch of these things, this is how you do it. You do all of them plus, then you do a minus of 2, then you do a plus of 3, then minus of 4, and so on and so on. So you calculate all these ahead of time. So let's just look at the code. I think I talked about it a lot. So we're going to sort our coins, and then for every single coin that a multiple of the coins exists, like I said, that multiple will only give you duplicates, so we can just toss that immediately to make our thing more efficient. Then we're going to try every number in a bit mask of 1 to 2 to the length of the coins, which will just give you a combination of active coins. Then we have our LCMs array. So basically all we do is we just check for every single bit. If it's on, then we will put the coin in. And then we do a LCM of all of these coins. So what this does in Python, kind of like in JavaScript, is like it's like a spread operator. So if you have like args as an array, this will basically call LCM with multiple things. So if you had LCM of like 1, 2, 3, it would just spread it out. So it'd be like LCM 1, 2, 3, 1, 2, 3. It'd be like that. So you get your LCM, and then you just check, is it odd or even length? And for odd length, you want to have it positive, and if it's even length, you want to have it negative. And then you just, so like I said, this is, or I didn't say it, but this is pretty bad naming. But essentially, duplicates is going to contain every single combination of LCM values, positive or negative. Then we have a function called numamounts, which will try a guess, and it will go through all of our LCM stored. And if it's negative, then we will subtract our number divided by the LCM. And if it's positive, then we will add the number divided by the LCM. And that's what we'll return. So then the rest of it's pretty straightforward. You just do a binary search from 1 to min coins times k. Like I said, that's the upper bound. And then basically you just want the minimum the minimum guess that gives you coins greater than or equal to k, and that's guaranteed to be your answer. You don't have to check like if it's a valid amount. The minimum will always be the best. And that's pretty much it. And so the main thing is I pre-computed LCMs because you're just going to be basically computing LCMs over and over and over. So you might as well just pre-compute everything. And you can also get rid of the coins that are multiples of other coins for efficiency. And so that's going to give you like the fastest. I mean, maybe it'll be like, yeah. So essentially, if we want to talk about runtime here, you basically have every single combination of coins, worst case. So that's going to be like 2 to the 15th or something, I think. So runtime, it'll be like of 2 to the number of coins plus log. So the rest of it will be pretty fast because the number of coins is pretty fast. So this will be something like log of I think this is like the biggest number you can have, right? So log of whatever, k times min coins times like the number of coins or something like that. But the number of coins like 20, so this will easily pass. And then space. So you have all your LCM combinations, and I think that's it. Yeah, so all your LCM combinations is like 2 to the coins worst case, which is fine because like there's only like 15 coins or something, or yeah. So it'll easily pass, and there's also it's very likely for some coins to be multiples of other coins and so on. Yeah. Okay, so let's look at the last one. So this one is definitely kind of hard for sure, and there's a lot you have to know. You have to know LCM, GCD, and this like inclusion exclusion that I didn't know ahead of time, so I had to look that up. So let's get rid of all of this. Hopefully this picture and the stuff that I said makes sense. You can look it up if you need some more clarification, or I'll also provide the code. Okay, so this one is actually pretty easy once you recognize one thing. So let's take a look. All right. And let's move this over here. Okay, so essentially you have an array of numbers, and then you have these AND values. And they basically tell you you can split your numbers into arrays such that whatever array you picked, like the first array has to have the AND of all the values in it be the first thing in AND value. So they kind of tell you in this example. So you split your array in the first one into 1 and 4 because that's like the only way to do it. So when you have 1 and 4, 1 and 4 gives you 0, which is this. So that's a fine split. So you have 1 and 4, and then the second array is a 3, which gives you a bitwise AND of 3. Third array is a 3. Fourth array is a 2. And then the total of each array is just the last value in the array, however you chose to make the split. So here it's going to be 4 plus 3 plus 3 plus 2. In the second example, they showed you all the ways you can divide. So here you split array into 235, and 235 ANDs to 0, apparently. And the total here would be 5. Then the second array is 3 sevens, which ANDs to 7. And then the third array is a 5. So the sum here is 17, and here's the other two ways. So the best split is like this. And then there's also sometimes you're not going to be able to split it at all. So like here, there's only one AND value, and when you AND all these together, I think you get 0. So there's no way to do this. And num's length is 10 to the 4th. So a really easy solution if num's length was a little bit smaller is like an n squared solution, where you just, for every single starting point, like you just do a DP, and then you just like loop as far as you can. But that doesn't really work, right? So you start at a number, and then you just loop as far as you can and try to split at every single index possible. You can obviously have some like short, some early termination. Like let's say you're trying to get a 7, but you have a 0 AND value, then you can like stop there. But, if all your values were like 7 in the entire array or something, you'd basically have like an n squared solution. So this is a little bit too slow to be n squared. So the main thing you have to recognize is you can actually have a DP solution of like the take or not take coin solution. So instead of like looping, you just say for each coin, I either put it in my current array and I keep going, or this will be the end of an array and then I'll make a new array afterwards. And those are your two choices. because you have to use, so I guess not coin, but each number, because you have to use every number. And to do that in DP, you need 3 things. And this might seem like it'll give you TLE, but it actually doesn't, because there's a couple observations you have to realize. So the 3 things you need, so if we have state here, so we need the index, that one's kind of obvious. Then we actually need a, so I just called it like a bit mask, but basically you need your current like AND value. And then you need your number of arrays that you have. So the number of arrays is fine because there's only, the AND value is only 10. So there's not that many, like you only split into 10 arrays. But the bit mask, basically the biggest number you can have is, at least the number you want to start at, is whatever your biggest number in here is. So if your biggest number is 10 to the 5th, you need all ones to cover 10 to the 5th. Because essentially what you want for your initial, well, I guess that's not true. So the biggest number you will have as a bit mask will be a 10 to the 5th. And you might think like, well, if that's 10 to the 5th, like if this is 10 to the 5th, and this is 10 to the 4th, surely that will fail because this is 10 to the 9th. And like normally in DP, you just multiply all your states together and this is 10. So this will be like 10 to the 10th and this will fail. But there's actually way less combinations of possible bit masks because you can only AND numbers, and you can only AND numbers that are right next to each other. So you don't have a lot of choices, and when you AND numbers, they get really small really fast. And also AND only gets rid of ones, it can't like add ones back. So there's actually like, in reality, there's way less combinations than this, and that's why it passes. Because when you AND numbers, like you'll start out with, you basically want to start out with a bit mask that's all ones, so that way when you AND your first number, it'll give you the first number. So like let's say I have like this, if I have a bunch of ones and I AND that with like 5, I'll just get 5. So that's kind of the idea. You want your initial bit mask to just be a big enough number of ones so you can make it like a 32-bit int, or you can just figure out like how many ones do I need to cover 10 to the 5th. I think it's like 1 to the 17th or something, or 1 shifted over 17. So like 2 to the 17th, I guess. But basically that's the main realization here, is the number of bit masks you'll have is actually significantly less than 10 to the 5th. Because you'll have some mask, and basically when you AND it with a number, there's a couple things that can happen, right? You can either AND it, like let's say you AND it with the biggest number possible. I don't know what 10 to the 5th looks like, but it's like, it's like 5 ones or something. So already, you know, if I have like 32 of these, and I AND it with like 5 ones, I'll basically get a bunch of zeros and 5 ones in some order. And then the only thing this can change to is getting rid of more ones. But now there's not that many combinations, right? So you can see like after one AND, it turned to this, and then after one more AND, I can only take a couple of these ones and turn with zeros. There's not that many combinations. So that's kind of the idea, is there's way less masks than this 10 to the 5th. So because this is actually in reality a lot smaller, this will pass. So now that you know that like this will pass, let's talk about like how we can actually get it to work. So for our base case, this one's pretty easy. Basically, we need arrays to equal the length of AND values. So AND values. And we need our index to be out of bounds. So equals length of like our nums. If this is true, the total we should return here is 0. And then anything else is just, we can just return infinity because it's invalid. And then our recursive case is pretty easy. So for our current number, we basically have a choice. Either add it to our current mask. So first we do add the value to our current mask. So we have a current mask, we AND with this value. Then we check if our mask with this value ANDed to it equals what we want. Then we have a choice. We can either keep going with this array currently, or we can split it into a new array. And whichever one gives us the least is going to be our answer. But let's say we have our mask and we AND it with a current value, and that new mask doesn't equal the value we want, then we have to keep going, right? We have to keep like adding more to the array to get this value. You can also do like a bunch of short circuiting probably, like I said. So for example, if you have 0 and you're trying to get 7, that'll never happen, right? So you could do things like that. So you could say like, you know, if my number is like less than the number I'm trying to get, just return infinity or something. So you can definitely like optimize it further if you want to. But yeah, that's the main thing to recognize. So we can actually look at the code, and the code's actually pretty easy once you recognize that the number of masks here is pretty small. Like this is more of a easier hard problem, and this is like an 8-point problem. So I think the ways you're supposed to solve this are like significantly harder. You're supposed to like be opposed to some segment trees or some other crazy stuff. So let's take a look at yeah, the actual thing here. So here, like I said, we have our initial mask that's just going to be a bunch of ones, because that way when we have a bunch of ones and we AND it with some number, we will get that number. And I did this in like another problem as well. So we have an easy DP now. So we basically have an index, the current mask that we have, and the number of arrays that we made. So if we went through all our numbers and we have the right number of arrays, then our total sum of just this is 0. Anything else, we just return infinity to make it not work. We initialize our result to infinity, and we make a new mask. So the new mask is going to be our old mask and our current number. If the new mask equals the value we're trying to get, then we can try to say this is the end of an array. So if this is the end of an array, then the total here will be this value, right? Because the total of an array in this case is the last value in an array, and we just chose to use this one. And then our recursive state is just index plus 1, and then we start out with a new mask again, so our all ones, and then we have one more array. You can also space optimize this if you want to get rid of this I. I didn't really do it because there are way too many problems today. But you can see that like every time you have I plus 1, so you can space optimize to get rid of that. And then this is the other case. So the other case, we just say, okay, let's just keep adding this to our current array, and we minimize those two. So this recursive case is just index plus 1. We have our new mask that we calculated, and the number of arrays stays the same. We just return it. And our initial state is just index 0 with a bunch of 1s, and we have no arrays. Then we just check. If we got infinity, then there is no solution here, so we just return -1. Otherwise, we return what we got. And we can run this, and it does work. And like I said, you can optimize here. So I think the way you would do that is you can say that like if I think what you would do is you would probably say like if the new mask does not equal, if the new mask is greater than or equal to this AND values, then we can like do this. Otherwise, it'll never be the case, right? Because if we're trying to get a 7 and we have a 6, for AND our value can only get smaller. So I guess we can do that. So we could say like if new mask is greater than or equal to AND values arrays, because otherwise we're basically never going to get it. So I think this should work. Maybe it'll speed it up a bit. Let's speed it up a little bit. But yeah, there's probably more stuff you can do. But the main thing you can recognize is this mask can't actually be, 1 to the 17th. It's actually significantly smaller. There's not that many solutions. So there are a few DP problems like that, where if you look at the states, you'll think you get a TLE, but actually it's because it still works because you don't actually hit every state. So the realistic number here is nowhere near this. It's a lot less. Yeah, so I think people posted, I don't know exactly how they got it. So I think they said it was like, so I is like N, and then the mask. I think they said basically the actual time complexity for the mask is just the biggest number in the, so it's like log of max nums or something. Log of max nums. I'm not sure if it's exactly this small. Like I wouldn't be too sure about that, because it's basically like how many 1 bits are there in like the biggest number. I don't know about that. But I do think it's like significantly less than that, like I said. And then the number of arrays is like 10 or something. So this will be fine. And then space. So same thing, I think. Because for each one of these you have 2 decisions. So it'd be like this thing 2. And then, yeah, like I said, you can make the space, get rid of this if you want to space optimize, do bottom up, but I didn't really bother doing that. But yeah, it's kind of a long video, so I think I'm going to cut it here. If you have any questions, as always, let me know, and I'll post all the solutions, and hopefully this is helpful. So thanks for watching.